Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Waste Materials for Energy Conversion Pathways from paper Energy Related Materials. So students, let us see what we are going to learn in this module. From this module, we may get to know about the following things. First, what is waste and what type of waste materials and how their management is being done. Waste is a wide-ranging term including most unwanted materials like any scrap material, effluent, or unwanted surplus substance or article. Waste requires disposal as it is broken, worn out, contaminated, or otherwise spoiled. Waste are those substances or objects which fall out of the commercial cycle or chain of utility. For example, glass bottles that are returned or reused in their original form are not waste, whilst glass bottles banned by the public and dispatched for remolding are waste until they have been recovered. As per the Department of Environment norms, the waste is identified in four broad categories such as worn but functioning substance or objects that are still reusable for the purpose they were made. Second, substance or objects that can be put to immediate use otherwise than by a specialized waste recovery establishment or undertaking, for example, ash from a power station used as a raw material in building blocks. Third, degenerated substances or objects that can be put to use only by establishments or undertakings specialized in waste recovery. These are always waste even if transferred for recovery for value, for example, contaminated solvents or scraps. Such substances only cease to be waste when they have been recovered. And the fourth one is substance or objects which the holder does not want or which he has to pay to have taken away. If substances or objects are consigned to the process of waste collection, then they are waste, but they may not be where they are fit for use in their present form by another identified person. Thus, organization may dispose of the items of considerable residual value from production scrap materials to redundant plant and equipment which may fall within the legal definitions of waste and their control regimes. The Environment Agency is the legal body that controls certain types of waste called as control waste, which include household, industrial, and commercial waste. Other waste are non-controlled. Agriculture, mines, and quarries are not currently regulated in the same way. Certain wastes are classified as hazardous, which is a broad term for a wide range of substances that may have variable levels of risk. For instance, toxic substances that may cause cancer are classed as hazardous. Fluorescent tubes or cathode ray tubes in televisions are also classed as hazardous and pose little immediate threat but may cause long-term damage over a period of time. The Environment Agency identifies waste as substance or object that has been discarded, is required to be discarded, or is intended to be discarded. The word discarded has a broad meaning and includes those things that are going to be replaced or recovered. The framework detailed in the given figure gives the reader a general overview of different types of waste. Further, we can classify this waste as control waste and non-control waste. Now, the control waste includes households, industrial, commercial, and clinical. And amongst these, there are two types of waste, and These can also be classified further into hazardous and non-hazardous waste. Now, under the category of non-controlled waste comes agriculture, radioactive and explosives, which are again either hazardous or non-hazardous. Now, let us see the classification of waste. A clear appreciation of the quantities and characteristics of the waste being generated is a key component in the development of robust and cost-effective solid waste management strategies. However, amongst developed countries within the region, the quantification and characterization of waste forms the basis for management and intervention. Elsewhere, little priority is given to the systematic surveying of waste arising and the quantities, characteristics, seasonal variation and future trends of waste generation are poorly understood. Moreover, there is a lack of comprehensive information at the country. Some broad trends and common elements are discernible. Generally, the developed country produce huge quantities of waste per capita compared to the developing countries. However, in certain circumstances, the management of even small quantities of waste is a significant challenge. For example, in a small island of South Pacific subregion, small population and modest economic activities have ensured that relatively low quantities of waste are generated. However, many of these countries, particularly small atoll countries such as Kiribati, Tuvalu and the Marshall Islands, face considerable waste management challenges due to their small land area and resultant lack of disposal options. Throughout the region, the principal sources of solid waste are residential, households and the agriculture, commercial, construction, industrial and institutional sectors. Now let us see these sources one by one. First is the residential source of waste, and the typical waste generated is single and multi-family dwellings, and the types of solid waste are food waste, paper, cardboard, plastic, textiles, leather, yard waste, wood, glass, metal, ashes, special waste like bulky items, consumer electronic, white goods, batteries, oil, tires and household hazardous waste. Second category of sources is industrial. Now, light and heavy manufacturing, fabrication, construction site, power and chemical plants are the waste generators. And the typical solid waste are housekeeping waste, packaging, food waste, construction and demolition material, hazardous waste, ashes and special waste. Now, the third category is commercial waste, where the types of generator are stores, hotels, restaurants, markets, office buildings, etc. And the types of solid wastes are paper, cardboard, plastics, wood, food waste, glass, metals, special waste and hazardous waste. Next category is institutional, where the generators of these waste are schools, hospitals, prisons, government centers, etc. And the types of solid waste are same that we are seeing in the commercial waste. Now next is construction and demolition. New construction sites, road repairs, renovation sites, demolition of buildings are the types of waste generators, and the types of waste solids are wood, steel, concrete, dirt, etc. Next is municipal services. Now the types of waste generators are street cleaning, landscaping, parks, beaches, other recreational areas and water waste treatment plants. And the types of solid waste are street sweepings, landscape and trees trimming, general waste from parks, beaches and other recreational areas and sludges, etc. And the last source is the process, where the waste generators are heavy and light manufacturing, refineries, chemical plants, power plants, mineral extraction and processing. And the types of solid waste are industrial process waste, scrap materials, off specification products, slag and tailing, etc. Now students, you can see in the video there is a table which summarizes the different types of waste and the sources. For the purposes of this review, these sources are defined as giving rise to four major categories of waste. First, municipal solid waste. Second, industrial waste. Third, agricultural waste. And fourth, hazardous waste. Now let us study about these sources of waste in details. So let us see the first category, which is municipal solid waste. Municipal solid waste or MSW is generated from households, offices, hotels, shops, schools and other institutions. The major components are food waste, paper, plastic, rags, metals and glass, although demolition and construction debris is often included in collected waste, as are small quantities of hazardous waste such as electric light bulbs, batteries, automotive parts and discarded medicines and chemicals. Generation rates for MSW vary from city to city and from season to season and have a strong correlation with levels of economic development and activity. High-income countries such as Australia, Japan, Hong Kong, China, Republic of Korea and Singapore produce between 1.5 to 5.0 kg per capita per day. Middle-income countries such as Indonesia, Malaysia and Thailand produce between 0.5 to and 1.0 kg per capita per day, whilst low-income countries such as Bangladesh, India, Vietnam and Myanmar have generation rates of between 0.45 and 0.89 kg per capita per day. Now students, you can see a bar graph on the video which shows the MSW generation by the high, middle and low income countries of the region. Taken as whole, the Asia and Pacific region currently produces some 1.5 million tons of MSW each day, and this is expected to be more than double by 2025. The current estimate for waste generation may be considered as extremely conservative. The actual levels are probably more than double this amount. You can also see from this bar graph that the current contribution of various sub-regions to the waste generated by the region. Now the composition of municipal solid waste varies significantly across the regions, with some middle and low income countries generating waste containing over 70% organic content, with corresponding moisture content in excess of 50%. This you can see from the bar graph given on your video screen. Differences in the characterization and reporting of waste type also differ, with some municipal authorities including construction and demolition waste and industrial waste as part of the municipal waste stream. Some inter-urban differences relate to climate and fuel use. The cities where heating is needed in winter, such as Beijing, Shanghai, Seoul and Tokyo, and where coal is the main source of energy, have much greater amount of ash in the waste in those cold months. The basic infrastructure brings other variations in cities and towns such as Calcutta, Dhaka and Hanoi, with unpaved or poorly paved streets that have large amounts of dust and dirt from street sweeping. There are big differences in amounts of organic waste and among cities according to the number of trees and shrubs in the public places. Large and bulky waste items such as abandoned motor cars, furniture and packaging are found in the higher income economies such as Brunei, Darussalam, Japan, Republic of Korea and Singapore, but not in low income countries such as Bangladesh, Cambodia, Myanmar, Nepal, Sri Lanka and Vietnam. Now students, next category of waste is agricultural waste. Agricultural waste therefore includes a range of waste streams that originate from agriculture or horticultural establishments. For example, agricultural plastic and packaging waste, empty pesticide containers, clinical waste, tires, old machinery and oil. Certain waste derived from agricultural premises are subject to strict control under the animal byproduct regulations. for example carcasses and some bedding materials, or may subject to control under clinical waste, special waste, or radioactive waste legislation. Now, expanding agricultural production has naturally resulted in increased quantities of livestock waste, agricultural crop residues, and agro-industrial byproducts. Among these countries in the Asian and Pacific regions, People's Republic of China produces the largest quantity of agricultural waste and crop residues, followed by India. In People's Republic of China, some 587 million tons of residues are generated annually from the production of rice, corn, and wheat alone. So next category of waste are industrial solid waste. Industrial solid waste in the Asian and Pacific region as elsewhere encompasses a wide range of materials of varying environmental toxicity. Typically, this range would include paper, packaging materials, waste from food processing, oils, solvents, resins, paints and sludges, glass, ceramics, stones, metals, plastic, rubber, leather, wood, cloth, straw, abrasives, etc. As with municipal solid waste, the absence of a regularly updated and systematic database on industrial solid waste ensure that the extract rate of generation are largely unknown. Industrial solid waste generation varies not only between countries at different stages of development but also between developing countries. In People's Republic of China, for example, the generation ratio of municipal to industrial solid waste is 1:3. In Bangladesh, Sri Lanka and Pakistan, however, this ratio is much less. In high-income developed countries such as Australia and Japan, the ratio is 1:8. However, based on an average ratio for the region, the industrial solid waste generation in the region is equivalent to 1900 million tons per annum. This amount is expected to increase substantially, and at the current growth rates, it is estimated that it will double in less than 20 years. As the existing industrial solid waste collection, processing and disposal systems of many countries are grossly inadequate, such incremental growth will pose very serious challenges. Now let us see next category of waste is hazardous waste. With rapid development in agriculture, industry, commerce, hospital and healthcare facilities, the Asian and Pacific region is consuming significant quantities of toxic chemicals and producing a large amount of hazardous waste. Currently, there are about 1 lakh types of toxic chemicals commercially available. Each year, another 1000 new chemicals are added to the market for industrial and other uses. The availability of robust data on the generation of hazardous waste for the Asian and Pacific region is limited by liability of information on the quantities and types of hazardous waste produced at the country level. This is due to a variety of reasons, including the lack of qualified personnel to undertake the necessary assessment, the reluctance of industries to provide process information, including waste arising data, and a poor appreciation of the extent to which generated waste is hazardous. Where data is available, significant difficulties are encountered in seeking to draw international comparisons due to differences in classification and definition of hazardous waste from country to country within the region. Most hazardous waste is the byproduct of a broad spectrum of industrial, agricultural and manufacturing processes, nuclear establishments, hospitals and healthcare facilities. Now let us see what is waste management and how is it done. Solid waste management is one thing just about every city's government provides for its residents. While service levels, environmental impacts and cost vary dramatically. Solid waste management is arguably the most important municipal service and serves as a prerequisite for other municipal actions. Currently, world cities generate about 1.3 billion tons of solid waste per year. This volume is expected to increase to 2.2 billion tons by 2025. Waste generation rates will more than double over the next 20 years in lower income countries. Globally, solid waste management cost will increase from today's annual $205.4 billion to about $375.5 billion in 2025. Cost increase will be most severe in low economic countries, even more than five-fold increases, and lower middle income countries where more than four-fold increases. The global impacts of solid waste are growing fast. Solid waste is a large source of methane, a powerful greenhouse that is particularly impactful in the short term. The recycling industry, with more than 2 billion informal waste pickers, is now a global business with international markets and extensive supply and transportation networks. Locally, uncollected solid waste contributes to flooding, air pollution, and public health impacts such as respiratory ailments, diarrhea, and dengue fever. In low-income countries, cities where solid waste management is usually a city's single largest budgetary item. Managing these solid waste streams well and affordably is one of the key challenges of the 21st century. Traditionally, municipal solid waste management includes the functions of collection, transportation, resource recovery, recycling, and retreatment. The primary goal of MSW management is to protect the health of the population, promote environmental quality, develop sustainability, and provide support to economic productivity. In addition, climate changes has drawn attention to the diversion of biodegradable municipal solid waste such as kitchen and garden waste from landfills because it has the potential to form a methane, which is a very powerful greenhouse gas under anaerobic conditions. According to the US Environmental Protection Agency EPA, the four basic options for integrated solid waste management include: first, source reduction including reuse; second, recycling and composting; third, combustion, waste to energy facilities; fourth, landfills. Examples from Denmark and Japan suggest that a sustainable waste management system furthermore consists of a stable mixture of technologies and institutions which work flexibly under a defined policy umbrella. Such sustainable waste management systems are designed to mimic an ecosystem that is robust and resilient. Taking a system perspective can help to example determine whether materials currently regarded as waste in one industrial sector could be viewed as raw material by another sector. Every substance extracted from Earth's crust or harvested from the forest, fisheries, or agriculture is a potential waste. It soon becomes an actual waste in almost all cases, with a delay of few weeks to a few years at most. Materials consumed by the economic industrial system do not disappear. They are merely transformed to less useful forms. Waste Watch estimates that for each ton of household waste, 5 tons of waste is produced in manufacturing and 20 tons in raw material extraction phase. The Environment Agency estimates that 90% of all resources we consume are either thrown away or waste or discarded into the environment as effluent or air emissions. The focus on resource consumed is an important element in the drive for eco-efficiency. Therefore, there has been a move towards viewing waste as not only the traditional municipal and controlled waste but also as resources that can be recycled, recovered or reused. Now let us see what are the future perspectives for sustainable waste management. Ecosystems provide the best example of a system that works in a sustainable fashion. One of the central principles in industrial ecology is the vision that industrial systems can use materials extracted and metabolized in a cyclic manner driven by renewable energy, which is used in a cascading manner. One important measure relates to the systematic reuse of waste products in order to minimize the need to extract virgin raw materials and deplete environmental services. However, to date, recovery rates for materials such as metals, plastic, paper, etc. from the municipal waste stream vary widely, even amongst industrialized countries also. For example, in Germany in 2007, a total of 25% of all municipal solid waste generated was disposed to landfills and incinerators, while in the US, a total of 67% of all municipal solid waste generated in 2008 was discarded. Furthermore, the EU landfill directive sets targets to progressively reduce the amount of BMSW disposed to landfills amongst the EU member states, whereas in the United States, large amount of organic waste are sent to landfills. This happens despite the fact that organic waste, being rich in carbon, could serve increasingly as feedstock for thermal and biological processes, recovering the carbon for further use as chemical feedstock, that is carbon recycling. The concept of carbon recycling is that instead of releasing the carbon stored in biowaste into the atmosphere by applying conventional waste management practices such as incineration for heat or anaerobic digestion and landfilling for biogas, landfill gas, the carbon inherent in the organic waste should be seen as a valuable feedstock resource. Instead of carbon capture and storage, which generally occurs at the beginning of resource flows, example at oil extraction sites to reduce fossil GHG emissions, the principle of carbon capture and reuse could be further developed and applied throughout the whole socio-industrial metabolism. Specifically, technologies such as gasification, which allows the generation of a syngas, or anaerobic digestion for a generation of an upgraded biogas like methane, could be applied. Both syngas and biogas can then serve as feed, example for the Fischer-Tropsch synthesis to produce base compounds such as Fischer-Tropsch, naphtha, and a number of subsequent chemical products and fuels. In addition, hydrolysis followed by fermentation can be applied to generate a variety of different base chemicals. When fuel, for example FT diesel, methanol, ethanol, etc. are produced from organic waste and oxidized by use in combustion engine, the carbon which has been originally captured in the waste feedstock is emitted back to the atmosphere. Now, assuming that the system-wide environmental burdens along this process route are lower than those of conventional fossil-based fuel production routes, this process route would lead to a mitigation of environmental burdens. However, this route of using carbon as fuel is still a linear process through the socio-industrial system, which depends on significant amount of waste feedstock available. If in contrast, synthetic material for the production of plastics could be synthesized, then the carbon would be kept longer in the use phase and add to the stock of durable goods in the technosphere. The plastic products could potentially be recycled at the end of cycle to provide feedstock for either energy generation or as feedstock for the production of syngas in cascading use scheme. The concept of carbon recycling, making use of organic waste as feedstock for polyolefins production. For the example of Fischer-Tropsch synthesis, from an environmental perspective, the use of waste would be advantageous, such as in comparison to virgin green wood biomass, it has no direct land use requirement and collection and processing systems are oftentimes already in place. In addition, thermal treatment like gasification has the further advantage of contributing to volume reduction, waste disinfection, and concentration of certain toxic elements, for example cadmium, in the gasification ash and slag produced. A comprehensive systems analysis is required to assess the life cycle wide performance of carbon recycling compared to conventional systems of waste management. So, students, let us summarize what we have learned in this module. Managing these solid waste streams well and affordably is one of the key challenges nowadays. Traditionally, municipal solid waste encompasses the functions of collection, transportation, resource recovery, recycling, and treatment. The primary goal of MSW management is to protect the health of population, promote environment quality, develop sustainability, and provide support to economic productivity. In addition, climate change has drawn attention to the diversion of biodegradable municipal solid waste, such as kitchen and garden waste, from landfills because it has the potential to form methane, which is a powerful greenhouse gas under anaerobic conditions. According to the US Environmental Protection Agency, that is EPA, the four basic options for integrated solid waste management include source reduction, including reuse, recycling and composting, and combustion, that is waste to energy facilities, and fourth one is the landfills. Now, examples from Denmark and Japan suggest that a sustainable waste management system furthermore consists of a stable mixture of technologies and institutions which work flexibly under a defined policy. Thank you.